On this video, let's talk about telescoping series. A telescoping series is any series where the partial sums telescope or collapse, what we call collapse, in upon themselves, leaving a sequence of partial sums that we can actually evaluate. So what we're going to do is we're going to use our algebra, our rules of logs, our partial fraction decomposition, those sort of things to determine how these sequence of partial sums telescope and then actually look at that limit of the partial sums. So that's what we're going to do. And what we want to remember is that is building off of the theory that a series will converge when its sequence of partial sums converges. So we're going to take a look at those partial sums. We're going to build a sequence of partial sums. And if that converges, then of course the series itself is converging. So let's take a look at this first example. So we've got an example. It is the series from k equals 1 to infinity, the sum from k equals 1 to infinity of 1 over k squared plus k. So what I'm going to do here is first just think about what do the partial sums look like. The partial sums look like. So what is a partial sum? Well, a partial sum is the sum from k equals 1 to n of those terms, 1 over k squared plus k. So we're going to be looking at those partial sums. Well, what can I do here? How could I simplify this? How am I going to see that this is actually going to collapse? So there's a little algebra I got to do here first. So what I look at here is partial fraction decompositions, because I can see that the denominator is going to factor k times k plus 1. I'm going to zoom in a little bit here. There we go. K times k plus 1. And so I'm going to say, well, I know through partial fractions that this is a over k plus b over k plus 1. And then let's just come off to the side, do our little side work to figure out what are a and b. So some side work out here, going back into some of our integration strategies and some algebra, and I can see here that 1 over k squared plus k is equal to a over k plus b over k plus 1. So 1 multiplying by, you know what, I'm actually going to write that in its factored form, k times k plus 1. Multiplying by the common denominator there, we get a times k plus 1 plus b times k. I'm going to use just the method of useful x values here to find my a and my b. This is a quick, fairly easy partial fraction breakdown. Useful x's. Using my useful x's, if x equals 0, then 1 equals a times 1. And actually, I said useful x's, but let's use useful. They're k's in this case. Useful k's. A is 1, and if k equals negative 1, b times negative 1, b is negative 1. So we've got 1 and negative 1, and I come back to my partial sum up here. So S sub n is actually equal to the sum from k equals 1 to n of 1 over k, and b was negative 1, so negative 1 over k plus 1. Now, notice what's happening here. I've got a positive and a negative. I've got k and k plus 1. So when I start to write out, let's write these out so we can actually see the telescoping. When I start to write out the terms in this sequence of partial sums, when k equals 1, the first term in the partial sum is going to be 1 over 1 minus 1 over 2. And then the next term in the partial sum when k equals 2 is going to be 1 over 2 minus 1 over 3. Then the next term at k equals 3 is going to be 1/3 minus 1/4. And I'm going to just go a little further. I think we can see some canceling of terms here, but let's go to k equals 4. We get 1/4 minus 1/5. We're going to go as far as we need at the front of the series, at the front of the terms in the partial sum, and then we're going to end at the end when k equals n, so we can see the collapsing on both sides of this partial sum. So when k equals n, we'd have 1 over n minus 1 over n plus 1. the term before that, when k equals n minus 1, we'd have 1 over n. I'm going backwards actually here. I should have started at the beginning. We'd have 1 over n minus 1 over n, and so on and so forth. It would back it out. So I think we have enough terms. I'm expanding this out so we can really see the collapsing here. But I think we have enough terms that we can see how this telescopes, how it collapses upon itself. This partial sum, notice we have a negative 1/2 in the first term, but then we have a positive 1/2 in the second term. We have a negative 1/3 in the second term and a positive 1/3 in the third term. And you can see that this is going to collapse. We didn't put the fifth term right here, but we do know that it has a 1/5 in it based on the pattern. And then we go to the end and we see a similar canceling. We have this 1 over n in the last term, and in the term before it, we have a negative 1 over n. So those are going to cancel. Now, I didn't write the n minus second term right here, but we do know that it has an n minus 1 based on the pattern. So we know that that's going to cancel. So all the terms, so each of the terms in this partial sum, each of the terms have, when we break it out into its partial fraction decomposition, each of the terms have two numbers in them, and one of them is going to cancel except for in the very first term and in the very last term. And so our partial sum totally collapsed down upon itself so that the partial sum became just 1 minus 1 over n plus 1. So we actually have, notice what that is. That's an explicit formula for the partial sums, for the sequence of the partial sums. And if we have an explicit formula for the sequence of the partial sums and we want to know if it converges, all we have to do now is take the limit of those partial sums as n goes to infinity. So what is the limit? Does this have a limit? Does this converge? The limit as n goes to infinity of s sub n is going to be the limit, because it collapsed all the way down to just two terms, of 1 minus 1 over n plus 1. 1 over n plus 1 as n goes to infinity is going to approach 0, and this becomes 1, which is a finite value, and this definitely converges. So we can see that this series that we're looking at converges to 1. I'm trying to get it all on the screen right here. It definitely converges to 1. So therefore, the series from k equals 1 to infinity of 1 over k squared plus k is actually equal to 1. It converges. That has a finite sum. That infinite sum, that infinite series right there, converges down to just 1. Okay, let's look at one more on this video and see what happens. So let's look at this guy. This one, we have a natural log. We're taking the series of terms, the natural log of k plus 1 over k plus 3. And let's see what happens here. So I'm looking at that one and I'm thinking, okay, what sort of algebra could I do? I'm told that this is a telescoping series, so let's use some algebra. And the algebra I want to use is rules of logs. I've got some logs in here. I've got a quotient. So let's break this down into, well, let's first look at the partial sums. Let's write it in partial sum notation first. So S sub n is equal to the sum from k equals 1 to n. And when I write the partial sum, I'm going to go ahead and just write this out. Natural log of k plus 1 minus the natural log of k plus 3. So I go ahead and I write that out and I say, okay, so that's what the partial sums look like. And I notice here, that what's going to make this collapse is I notice that I have a positive natural log of k plus 1 where the index is k plus 1, and then I'm subtracting a natural log of k plus 3 where the index is shifted 2 units over. And that's what's going to create that collapsing when I start writing out these terms. So let's see what these terms look like. I'm going to go ahead and fast forward the video and just write out a bunch of terms, and then we'll come back and you'll be able to see the collapsing of the terms. Okay, so I wrote out all those terms, and now we can start to see the collapsing. So because of the shift, there are 2 units between k plus 1 and k plus 3. There's 2 units. So notice that the shift is not in the terms that are directly next to each other, but we actually skip a term. So right here you can see that the natural log of 4, we have minus the natural log of 4 in the first term, and then we have positive natural log of 4 in the third term. But those will cancel with each other. They will telescope and collapse. We have the negative natural log of 5 in the second term, and then positive natural log of 5 in the fourth term. And so what's going to happen is this natural log of 6, we didn't write in the next term, but we do know that it's going to cancel because, 2 terms out, that will cancel. So that's going to cancel, and that's going to cancel. So we end up being left with 2 terms in this expansion of the partial sum. We have the natural log of 2, and we have the natural log of 3. And then we notice on the tail end, so I also wrote out 4 terms. I wrote out a lot of terms so we could really see what's happening here. We notice that on the tail end that we have some similar patterns happening. In the very last term, we have a positive natural log of n plus 1, but 2 terms before that, we have a negative natural log of n plus 1. So those are going to cancel. Then we have the we have the positive natural log of n, and we have negative natural log of n. So those are also going to cancel when we go, 2 terms. We have to look back 2 terms to get that canceling. And that is going to happen for all of the terms. We didn't write in this term here. We didn't go back 5 terms back, but we know that the natural log of n minus 1 will also cancel, and the natural log of n minus 2 will also cancel there too. There will be a negative corresponding term a couple terms back in the expansion. So if we have 2 terms left in the beginning because of the way that these patterns are arising, we know that we will also have 2 terms left at the end. And so this partial sum, S sub n, becomes the natural log of 2 plus the natural log of 3 minus, we just collect the terms that are left, natural log of n plus 2 minus the natural log of n plus 3. And just using, because I know I want to take the limit of this, so using some rules of logs, I'm going to combine terms a little bit here. This becomes the natural log of 6, and then we have minus the natural log, this is actually minus the natural log of n plus 2 times, pull the minus all the way out, n plus 2 plus the natural log of n plus 3. So then we can pull those together. This is the natural log of n plus 2 times n plus 3, all inside of a natural log. And we could even bring that all together. This is the natural log of 6 over, and I'll expand that while I'm at it, n squared plus, let's see, we get 5n plus 6. Okay, so just because I know I want to take the limit, I guess we could have left it as it was, but in the limit, we're going to want it simplified. So I was using my rules of logs. We used our rules of logs in the beginning to break apart a natural log, and here we're using our rules of logs in the end to pull our terms all together into a single natural log. So now that we've been able to write an explicit formula, now we want to take the limit as n goes to infinity to determine if S sub n converges. So that's the question. So let's do it. So what is the limit of the partial sums? Now that I have an explicit formula for the partial sums, used algebra to get that, what is the limit of that partial sum? 6 over n squared plus 5n plus 6. And as we take the limit as n goes to infinity, what's going to happen here? Well, the denominator is definitely bottom heavy. We're going to get 6 divided by infinity squared plus 5 times infinity. This is going to be approaching, as n goes to infinity, this is going to be approaching 0. So we end up with the natural log of something that is approaching 0. Now it is approaching 0. It is all positive, so it is approaching 0 from the right. So what's happening to the natural log as the argument of the natural log is approaching 0? So just a quick reference to our little natural log graph. Let's think about what happens. Natural log of x. What is happening as our x's approach 0? Well, what's happening to the natural log is the natural log is decreasing without bound. This is going to negative infinity. And so since this partial sum, the sequence of partial sums is decreasing without bound, we say that the series itself is diverging. So this is diverging. So our series that we were looking at up here, our series diverges. And we were able to show that by breaking down the partial sums into a telescoping set, seeing how it collapsed upon itself, and then taking the limit of that explicit formula that we generated for the partial sums.